What is geometry? The geometry that describes the universe and everything in it. Well, it sounds a silly sort of question. You know, what else could it be other than straightforward, common sense Euclidean geometry? For example, if you have two parallel straight lines and you continue them on to infinity, then they would always stay the same distance apart. As for triangles, well, the sum of the angles of the triangle all add up to 180 degrees. And it doesn't matter what the shape of the triangle is or its size, you always get 180. As for circles, well, the circumference of the circle is 2 pi times the radius r. And again, it doesn't matter what the size of the circle is, you will always get 2 pi r. So that's Euclidean geometry. But there are situations where that kind of geometry doesn't work. And suppose, for example, you're trying to circumnavigate the globe. There you're confined to a curved surface, and Euclidean geometry doesn't work there. If we're to set up a geometry for this kind of surface, then obviously we need straight lines to start with, and obviously to some extent there isn't a straight line there, they're all curved. But if we choose as our definition of a straight line that it's the shortest distance between 2 points, and suppose we have 2 points, one there and another up there, then clearly there must be one line there which will be the shortest distance between those 2 points, and in fact it's this line here. It's a line of longitude. And in general what we find is that between any 2 points the shortest distance, the straight line, is the arc of a great circle being one that lies in a plane that passes through the centre of the sphere. So all these lines of longitude are technically straight lines, and so also is the equator. So we've got our straight lines then. How about parallel straight lines? Well, yes, we can take any pair of lines of longitude, let's take that one and that one, as they cross the equator, because we know that that angle there is 90 degrees, and so is that one there. So these two lines are parallel. So let's now extend those to infinity, or at least as far as we can get on this surface. And obviously what happens is that those two lines, they don't stay the same distance apart as they did before, they actually converge and intersect there at the pole. So that's the first big difference between geometry on a sphere and geometry that is flat. How about the triangle? Well, I've drawn a triangle on here. We need 3 straight lines, so I've chosen 2 lines of longitude, this one and that one, and for the third side I've chosen the equator. Right, now looking at the angles of that triangle, clearly this is 90 degrees, we've said that before, and so is that, so add those two together and that gives us 180. But you know, we've still got to add in that angle there, so whatever that might be, it's obviously going to end up more than 180 degrees, the sum of the angles of that triangle. In fact, that is true not only of this triangle, but of any triangle we draw there. It always comes out to be more than 180 degrees. All right, if you have a very tiny triangle, an absolutely sort of tinsy-wincy little triangle such that it covers an area which is more or less flat, then the sum will come out to be roughly 180 degrees. But it will still, strictly speaking, be a little bit more. Right, thirdly, what about a circle? Well, let me draw a circle on here, and to make things simple, let me just draw it to be the same radius as we had here. So we'll take the pole as being the centre of the circle, and I swing this round, and lo and behold, the circle happens to be the equator, right? So the equator is the circle of radius r that we had before. So now let's just compare the circumference of the flat circle of radius r with the one on this surface. Well, as you see, there's no comparison at all. The circumference of the equator is obviously much smaller than we've got here. And of course it has to be when you come to think about it, because you know, this radius is curved. And that's what one finds with all circles that we draw on this surface, that the circumference comes out to be less than 2 pi r, because remember, this is what is 2 pi r. So that is what we call spherical geometry. And as you see, it's very different from flat Euclidean geometry. But even that doesn't exhaust the possibilities. Just, for example, we had a surface like this, the kind that a horse flea perhaps would have to learn how to negotiate. A saddle shape, or as we sometimes call it, a hyperbolic shape. Well, again, the first thing we have to do is to identify straight lines. And again, we use the convention that it's the shortest distance between 2 points, so that gives us some straight lines. How about parallel straight lines? Well, there are a couple down here. That one and that one. They are parallel. And if we follow that through, well, you see that, again, they don't stay the same distance, and neither do they intersect with each other as they did on the sphere. They diverge. So that's a big difference from the sphere. Triangles, yes, I've got a triangle over there, and as you can probably judge without measuring it, that the sum of the angles of that triangle are going to turn out to be less than 180 degrees. All right, now you might think that I'm cheating a bit, because you might think, well, he's actually only got one decent straight line there. The other two are curved, and he's deliberately curved them in order to make the sum come out less than 180 degrees. But actually, that's just a trick of the perspective. If I swing things round a bit, you'll find that that straight line begins to look curved, and the line on the left now begins to be the one that looks like a straight line. So what I'm saying is that you must be very careful not to go by appearances and stick by the convention that these lines are the shortest distance between 2 points. And so, okay, with that triangle and any other triangle that I draw on here, the sum comes out to be less than 180 degrees, whereas on the sphere it was more than 180. Finally, how about a circle? Well, let me again draw a circle on our curved surface with the same radius as we had originally, and we'll take the point here in the middle as being our central point, and well, as you see, I've already drawn that circle in there. This is the circle. And so what I have to do now is compare that new circle with our flat one. If I just clip that in there. I think you'll agree that's a pretty good fit, that side. So let's swing the whole thing around and see how it fits on the other side. As you see, it doesn't. There really is a big difference there. And again, I'm not cheating. If I take our radius, you'll see that it really is a circle of radius r again. And as you see, it turns out this time to be very much larger than the circumference of the flat circle. So what this means is that on this surface, the circumference of a circle is greater than 2 pi r, whereas there it was less. Right, now you may be saying, well, why bother with all these different kinds of geometry? Well, the point is this, that it could well be that Euclidean geometry does not apply to the universe. Now, I glibly started off by saying that these two lines, if stretched to infinity, would remain the same distance. But how do we know that? You know, we've never actually ever stretched lines to infinity. As far as we know, if we actually did the experiment, we might find that they intersected like they did on the sphere, or diverged as they did on that hyperbolic surface. As for triangles, well, yes, if I measured these angles, I'd find that they come to 180 degrees, as precisely as I can measure it. But this is a small triangle, you know, compared to the size of the universe. And we saw on the sphere that if you had a very tiny triangle, then even there you would get roughly 180 degrees. What would happen if we had a huge and absolutely gigantic triangle? Suppose, for example, that's us on our galaxy, and we had another observer on a different galaxy, and yet a third one over there on another galaxy. And suppose each of us took lines of sight to the other two galaxies and then measured the angle between the two. And then somehow we pooled our results and added the three angles together. What would we get? Would it be 180, or would it be something somewhat larger, as we got on the sphere, or smaller, as on the saddle? We don't know. We haven't done it. And as for the circle, okay, it's roughly, as close as one can say, 2 pi r. But again, if we had an absolutely huge circle, what would we get then? We don't know. In fact, we do not know what the geometry of the universe is. It's one of the big problems of cosmology. Well, fortunately, we don't have to go out there and measure these huge triangles and circles. We can adopt a different tack. Instead, we can go for that feature of the universe which determines what the geometry shall be. And that's the density of matter and energy. Now, when we look at the matter that we can see and we add up the amount of it, the luminous matter tied up in the stars, it actually doesn't come to very much. The average density based on that is very small. It's a very dilute universe. And on that basis alone, one would assume that the geometry would be hyperbolic. But we have to be careful. As you know from chapter 2, luminous matter is not the whole story. There is also dark matter there. We can't see it directly, but there are indications of it, and those indications show that there's a lot of it. In fact, more of it than the luminous matter. And who knows? It could be that there's so much dark matter there that it actually tips the scale over so that the geometry becomes one of those other two. We simply do not know what the geometry is. But there's one thing we do know, and that is that this universe is expanding. And so whatever the geometry will be, it'll be an expanding geometry. Either spherical expanding geometry, or it could be flat expanding geometry, or it could be hyperbolic expanding geometry.